session on image texture and completion. I'm Manish Agrawala from Stanford University, and we have a great session of 5 papers. Since we're starting a little bit late, we'll just jump right into the papers. The first one is titled Programmable 2D Arrangements for Element Texture Design, and the authors are Hugo Loy, Thomas Hurtud, Romain Vernier, and Joël Tolo.
All right, thank you. Okay, ladies and gentlemen, good morning. I'm glad today to talk about this project we worked on with Thomas, Romain, and Joël. It's going to be about element textures. So element textures are distributions of small geometrical elements, such as these circles, which are distributed in a repetitive fashion inside a much larger domain. Element textures are used in a wide range of arts and technical domains, such as comics on the left for representing the snow, or technical illustrations, for instance, on the drawing on the right to represent the feathers. And it's also used in CG, for instance, in this street, where basically every single man-made material is actually an element textures, for instance, for the bricks. So it's used everywhere. And at this point, you could tell me, hey, Hugo, like such hype, element textures are used everywhere. And actually, no, it's not a hype, because element textures are very bothersome to draw. Take, for instance, this street. It's already dozens of hours of work. And guess what? Element textures are not even fun to draw. All right, there's this fun part at the start when you think and design your own wall pattern and how it's going to look in the end. But after that, the whole work is 90% repeating over and over again the pattern until the whole street is covered in bricks. So that's not fun. So when we submitted the article, I wanted to entitle it "No More of That." But the reviewers asked for something a little more specific. But the idea is there. We want to automate as much as we can this bothersome process, like leave the fun part to humans and give the bothersome part to computers. So if we want to do that, we need to first to have a good look at what this process looks like. What does it take to draw an element texture? So first, you have to draw individual geometrical elements. You also need to arrange them in space. And finally, you need to stylize them, which means giving them some rendering properties, whether it is colors, gradients, BRDFs, or the like. And there are actually pretty good commercial softwares already to draw and stylize elements efficiently. So the real target, the real repetitive task we want to kill is arranging elements in space. All right? So this is our user. This guy wants to produce element textures. That's his job. And we want to make a program that will help him producing the arrangement part of the texture. But how should we do that? What's the big rule that says, okay, this program will help this guy? What separates helpful arrangement programs from bothersome ones? And the one big rule is, if you want to help them, first, don't annoy them. That's the main picture, okay? And when it comes to arranging elements, it splits into 3 different rules. Your program should be expressive, which means it should address a very wide range of different arrangements, and there's a very simple reason for that. However your program is designed, it has a learning curve. And if your program doesn't help users in a very large number of slides, then it's not worth investing into that learning curve. Second, the program should be usable. It looks stupid, but it has to. So in particular, the inputs from the user should lead to predictable effects on the output on the right. And the final property the program should ensure is stationarity. So stationarity is just a complicated word for repetitive. Every single texture is repetitive, so the user wants to get repetitive stuff. So the program should ensure this property on the output. The user shouldn't have to perform manual actions to correct things and get the thing stationary. All right, so let's have a look at previous work and see how it holds up against this base of specifications. So first, there are predefined layouts which are implemented on most commercial software such as Adobe Illustrator. These ones are super simple. You draw individual elements, you drag and drop them into the editor, and the editor is going to generate a uniform, so left and center, or grid distribution on the right from these elements. So this is super easy to use, all right? But this is the least expressive method you're ever going to see because it only addresses two different kinds of arrangements and not the others. The widely known approach in academics is known as example-based approaches. So these approaches are very convenient because they ask you to draw a small exemplar of the arrangement you want to get, and they will analyze this example and synthesize a larger version of this arrangement inside the whole region you want it to fill. So this is very convenient for artists because everything you need is just a digital pen. But these approaches have two main problems. First, current algorithms fail to perceive the same things as we perceive. For instance, very strong alignments and clusters of elements. So when you want to make arrangements with such features, they will fail to reproduce that faithfully. And the second problem is even users disagree about how a texture can resemble another texture, so how the output should resemble the input. So a very good study about Miss Muraj and colleagues in 2013 proved that. So it's very difficult to build a single bi-exemplar method that will satisfy everyone. So that's it for the previous work in element texture generation. But if we have a look at other CG domains, so for instance, point-based textures, such as in the Substance software from Allegorithmic, or floral ornaments on the center, or tangle patterns on the right. All of these guys don't do element textures, all right? But they all share one common point, which is they don't give exemplars or the like to the computer to analyze. They give instructions to be very specific about what they want. And that's the approach we want to have for element textures. So basically, we're going to have a programmable approach, which means communicating with the computer. And such as in every communication task, you need to speak the right words to express what you want. And these words should ensure that the whole programmable system is expressive, so many different outputs, usable, so the words shouldn't be too complicated, and stationary. So, for instance, on one extreme, we could very well let the user with plain blank C++ and say, hey, with that, like take a rendering library with that, and now you can draw pretty much every texture you want. Very expressive, right? But the user is also left with a bunch of operators he doesn't care about. This is not usable. On the very other end, we could have one word for every single kind of arrangement the user could ask for. Okay? But that's pretty fine layouts. So it should be usable, but it wouldn't be expressive enough because you cannot combine the words together. So since people care only about what they perceive, maybe we should have a look at what humans perceive in textures. So for instance, in this texture, this is a good example because it melts everything that we perceive. Humans like to perceive different scales on textures. So for instance, the bigger elements, which are the blobs on the top, and smaller elements, which are the little curves inside each blob. Humans also are very good at distinguishing individual elements, such as one blob, as well as the topology of their relationships with the neighbors. So for instance, the top texture is a non-overlapping arrangement. In the bottom example, we could say an individual element is just one little curve, and the topology is different. It's touching the neighbor curves on each end. And the final thing people see very well in texture is the regularity of the patterns, whether it's very strongly aligned or not. So for instance, the top texture is irregular, and the bottom texture is very regular. All right? So it would be amazing if for each of the three perceptual features, if we could find one word corresponding to each, one operator corresponding to each, so that these words could be combined in a very expressive way, and if these words could ensure the stationarity of the result. So let's give it a try. we propose partition operators, which give very simple textures. Okay, you don't have the choice of how they look. You just have to choose between irregular on the top or regular on the bottom. Mapping operators that will convert the initial very simple geometry into arbitrary geometry that you want to have, for instance, the blobs on the top or the curves on the bottom. So these are going to set the individual elements as well as the topology. And finally, the combining operator, which will combine different scales of texture together. So here we are. All of these operators use planar maps as a data structure. I'm not gonna get extended on that. There are more details on the paper. And basically, these three words describe quite well how humans perceive textures. So let's have a look inside them. So partition operators basically give you the choice between 4 different very simple arrangements, whether they are irregular on the top or regular on the bottom. You can set up the density for each of them, or the orientation of the alignments for the regular textures, and that's it. So basically, these operators are very simple and are just a matter of choosing whether your pattern is going to be regular or irregular. And the good thing about them is that since they are very simple, they are tuned to make always stationary patterns. All right? So the output of these operators is stationary. The second one is the mapping operators, which are going to transform these very simple patterns into more complex ones with the individual elements you like. So a mapping operator is what separates the arrangement 1 on the left from the arrangement 2 on the right. Okay? And the user should have to specify the least possible things. It should be the simplest possible to specify this transformation between arrangement 1 and arrangement 2. And actually, the only thing the user needs to describe is what happens to a single face of this arrangement, like transform the face into a single blob, which is in purple here. All right? So the code for that, hey, it's a programmable approach, so you gotta write some code at some point. The code for that is very simple. You import the individual element you drew, all right? You rotate it randomly, and then you match it at the center of the face. And finally, the manner you say that the transformation between your arrangement 1 and arrangement 2 is the combination of this mapper all over the faces of arrangement 1 is by using the map to faces operator, which is the actual mapping operator. So this is a very simple transformation, getting from one simple face and just complexifying a bit the geometry. But here, you could write pretty much anything. Anything actually that preserves stationarity, which is only 3 very simple rules. You have to make only bounded neighborhood queries inside the arrangement. The execution of the mapper should be independent from the execution order, and it should only use relative coordinates. And within these rules, you can basically write whatever you want. It's almost like a shader, but for geometry. So for instance, you can play with existing geometry, such as shrinking the faces of this first arrangement. You can create new topological diversities, such as by rotating the faces of this arrangement. You can perform very low-level topological operations, such as face split or face duals. And finally, you can operate on all the types of geometrical primitives you can get in these planar structures. Or for instance, instead of playing with the faces, you can play with the edges. So this is the API that was used in the mapping operators for all the results you're going to see in this talk. So that's a pretty short API for a programmable approach. All right, the final type of operator is combining, which are going to combine different textures so that to set the scales of the ones and the scale of the others. So basically, they're pretty much masking and scaling operators. If you take these 2 input textures, which were made by partitioning and mapping, the 3 combining operators are union, inside, and outside, which are pretty much masks. All right, so that's the 3 words which which correspond to the three main kind of things we perceive in textures, and let's see what it gives. So in terms of results, this leads to a very expressive range of results you can reach. So from very irregular to semi-regular to completely regular textures, such as these Escher patterns. You can also represent a wide range of natural phenomena, such as bubbles and cracks. So to get a more quantified study of how expressive this system is, we did a small study from references, from artists, from the internet, and we tried to reproduce the arrangements that these guys designed by hand. And for every single of them, we could make it. So that's a good quantification of how expressive this system is. So you can apply that to CG, of course, painting on surfaces or even on BRDFs, right? And to talk a bit about usability of this system. This system's power is to be able to break very complex textures, such as the one on the right, into very simple steps so that you can get your mind at work, even before writing a single line of code. And the good surprise was even very novice users worked like that very naturally from the start. So we did a user study with 1 hour learning. And after 1 hour, we gave people the targets on the left, and we asked them to get the closest result as possible to this target. And although everyone didn't get the exact same arrangements as the result, which is almost impossible in 15 minutes, the good thing in the results of this study is that they all took the right path. They all made the right choices to converge towards this initial result. And everything after 15 minutes is a matter of tuning, like the orientation of the elements, all their scales, all the like. All right, so after this tool, what's next? Because the original problem was to help people making element textures. So there are a few steps more to do that. So first, one concern of this kind of method is speed. The most often you're gonna generate textures with thousands or dozens, thousands elements, and this is gonna take a lot of time. Mainly if you're using planar maps, such as what we do. These are very complex to compute. So we did, in my PhD report, a method to accelerate greatly the regular and semi-regular textures generation, but there's still work to do for the completely regular textures. The second thing is getting some spatial variations, which you are going to need for most of your texture generation, for instance, in cartography, but as well for CG. So we did that in an expressive paper in 2016. So you're welcome to go and see that. And finally, the amazing thing to get this thing mostly usable as possible would be to drop a little the control by programming only, which reduces greatly the set of users that will be able to use the system, by having more of a bi-exemplar control, like the one we talked about at the very start of the talk. Like, for instance, in mapping operators, instead of just encoding the geometry you want to generate or importing it from external files, you could control with a pencil what happens inside your textures, and that would be amazing. All right, that's the different steps we need to get a real tool to make great textures, great art, and great technical illustrations. Thank you very much.
So we have time for questions. Please come up to the mics. So maybe I'll start with one. So you mentioned at the end program synthesis by example.
Yeah.
Have you thought more about that, and how feasible that would be with your system?
Yeah. So there is a lot of surface to reach with this kind of problematic, but the most trivial things to explore first will be the parameters, the continuous parameters that tweak the behaviors of the mappers. So for instance, the element scale. or the elements deformation when you want to get some actual variations inside the individual elements geometry and make it depend on the actual structure of the arrangement. So that could be drawn instead of just be coded, which is much more bothersome. Yeah. Anyone else? Yep.
Silva, I was wondering, what kind of workflow would you recommend in case someone wants to generate, for instance, height maps, normal maps, or different kinds of texture starting from a pattern generated by your system? Thank you.
All right, thank you. So basically, if I understand well, the question is, we're generating only geometry, and how to process the geometry afterwards to get other kinds of data, right? So basically, any shading system, any image processing system could generate height maps or BRDFs from this raw geometry.
For instance, I was wondering for height maps, I guess you will need a system that respects stationarity, right? You could probably do it by modulus operations, right? You can ensure that on the right side of the texture, the height is the same as the left side, or something like that.
Yeah. So the funny thing inside the post-processing of this data is that the rules you need to respect to keep the stationarity you had so much trouble keeping in the first phase, these rules are pretty much the same than the mapping rules, like just basically getting local operations, which most shaders do. Thanks.
Okay, let's thank the speaker again.
Thank you.
I think it's just the mic out there. Okay. All right, so our next talk is titled Deep Correlations for Texture Synthesis, and the authors are Umri Sendik and Danny Cohenor.
So, okay, great. So, thanks for having me. I'm Omri from the University of Tel Aviv, and I'd like to present my joint work with Danny Cohenor, named Deep Correlations for Texture Synthesis. So, a bit of background. I'd like to begin by describing some texture attributes and describe what a texture synthesis algorithm is after. I roughly divide textures into either stochastic or regular. And for regular textures, they are quite commonly characterized by a typical scale for example, in this beehive wall shown here, the scale is a single hexagonal element. But we need to be careful. Some textures, which are regular, may not have a single scale in them. For example, this brick wall here, which has both the local, small, single element brick scale, but it also has a global scale, which requires us to preserve the diagonal purple line. Okay? So if we were to synthesize more of the same, we need to preserve this diagonal line, which is global. And the texture synthesis algorithm's goal is to synthesize an image of the same textured family, but not the exact same. We do not want to reproduce the input. So there's a lot of work on texture synthesis. I'm definitely not going to go into all of them, but briefly dividing them, I can briefly divide them into parametric versus non-parametric methods. Parametric methods usually require defining a sufficient statistic of a texture in order to attempt to impose on our newly synthesized result, while non-parametric methods usually operate on the pixels directly. Now, a difficulty of parametric methods is defining or coming up with these sufficient statistics. And in addition, our personal impression is that a limitation they usually depict is a lack of crispness in the final output result. A limitation of the non-parametric methods is in their ability to create variability in the result. This is due to the fact that they usually operate on the input pixels directly, meaning they copy the artifacts up onto the output result, and they effectively limit the variability. Another limitation is that they require defining a typical texture scale, just as I presented in the previous slide, which requires human involvement. Now, our method strongly builds upon Gattis et al. Style transfer work, so I start by really briefly describing it. The style transfer algorithm, what it attempts to do is to transfer the style from a style example, shown by the Van Gogh portrait here, into a different content image, such as the one shown by me here. It works by imposing an output image to have similar statistics as these two input images. And these statistics are defined as the Gramm matrix of the style image, calculated on features which were extracted from a pre-trained CNN, while the content statistics are simply the features themselves of the content image. And in order to impose, we simply minimize an L2 loss between these statistics. Now, if we take this framework, but we get rid of the content loss, okay, meaning there is no loss which imposes structure, then we can use this framework, we can use Gattis' framework for synthesizing textures such as the ones in these examples. This approach works quite nicely for stochastic or random textures, but obviously it fails on regular textures because the Gramm loss alone does not impose structure. Once we calculated the Gramm matrix, we lost any spatial information. For example, in the two upper stochastic textures, the results seem quite plausible, but in the two bottom ones, which are regular, the result seems much less plausible, and we attribute the failure to the lack of structure. We need some sort of proxy or structure proxy. So part of the novelty which we present in our algorithm is a new loss, which imposes structure, but differently than a simple L2 feature loss, it does not impose content. Okay, we name this loss the correlation loss. In essence, what it involves is extracting another statistic based on correlations of features. In the figures here, we show that for different crops of the same input texture, we yield similar correlation matrices, empirically proving that the correlation matrix does not impose content, but rather only structure. For example, on the left-hand side, we take two crops out of a metallic texture and extract its correlations. And we can notice that even though the crop is at a different phase of this metallic texture, or part of the metallic texture, the correlation matrix is similar, meaning that if we impose this statistic, we will not impose content but only structure. The correlation loss, in essence, involves calculating weighted correlations between the features which we extracted from our pre-trained CNN, and then we minimize the L2 loss between our example correlation metrics and our newly synthesized result. And by completely losing the coordinate information, which happens once we extract the correlation matrix, it simply has no location information, we do not impose content, but rather only structure. In this image, what I show is the result of Gattis et al.'s algorithm, which means we synthesize textures using the Gramm matrix only. And you may quite easily notice that structure isn't preserved properly. Now what I do is that I use the deep correlation loss. Okay, so here we show the result of using correlation loss instead of the Gramm loss, and see that structure is beginning to be preserved, but it's still far from perfect. Still many artifacts. And finally, in this example, what I show is the result of using both the Gramm loss and the correlation together, and the correlation loss together. And I depict the fact that these two losses are, in fact, complementary. They aid one another. Here I show the exact same images side by side, again, in order to show that they are complementary, and that using them together improves the results. Okay, so now what I want to do, I want to tell you about two insights which we found simply by trying out our algorithm a lot. And I'll lay down these two insights, and then following slides, I'll connect them into the entire algorithm. So by trying our new loss on a lot of input textures, we empirically found that adding the correlation loss is perhaps too powerful, and it may have the ability to reproduce unique details, such as the line in the black rectangle. You see it in the projector. And the dark spot in the yellow rectangle. In texture synthesis, we wish our output to be more of the same, but not the exact same. Okay? We do not want to reproduce this exact example. We want to have more results from the same family. So in order to refrain from reproducing the exact output, we tackle this problem by adding a loss which encourages diversity. Now this loss is exactly equivalent to Gattis' content loss, but only negated, because what we wish to do is grow distant from the input example's content rather than close to it. Our second insight is a new smoothness loss. By trying our new loss on a lot of input textures, we also found typical types of artifacts, such as checkers, which are most probably caused either by the CNN pooling or some sort of filter imbalancing inside the CNN. So a common approach for dealing with such artifacts is adding a total variation term, which is edge insensitive and hence tends to blur. So we tackle this by adding an edge-aware smoothness loss, which resembles a soft min function. The exponent effectively nulls the features with a larger distance between them, leaving only the most dominant term for the logarithm. In other words, it is sufficient for only one pixel neighbor to be similar in its value for this loss not to penalize. The images below, starting from left to right, show that as we strengthen this loss, the checkers start disappearing, but edge boundaries aren't blurred. Okay, so to recap, our entire algorithm involves optimizing over the weighted addition of these four losses, namely the correlation loss, the Gramm loss, the diversity loss, and the smoothness loss. The parameters of the algorithm are the relative loss weights and the layers from which features are extracted in order to calculate the losses. And please refer to our paper for details on the exact weight choices and layer choices. But we do emphasize that all of the results, both in our paper and in this presentation, were achieved using the exact same set of parameters. Okay, so no manual intervention. Okay, so finally, we show some of our results compared to Caspar from 2015, which is a non-parametric method mainly meant to cope with regular textures, to Gattis' algorithm, and to Portilla and Simoncelli's algorithm, which is a parametric texture synthesis one. Here we show that our algorithm works on regular textures without the need to define any explicit scale. Notice how we preserve structure, while the other algorithms do so less successfully. For example, in the bottommost result, the order of the bricks is either inconsistent or completely fails. And here we show that our algorithm works also on stochastic textures without the need to change any algorithm setting. In all of the algorithms we compared, it's an important issue, in all of the algorithms we compared to, we make use of the author's proposed configuration. So notice, for example, that in the middle result, we properly preserve the snake skin line in the middle, which is a structured component, while at the same time we properly synthesize new snaky textures, okay, which are sort of stochastic. And again, the same settings, no manual intervention, works properly both for stochastic and regular textures. Okay, well, this is the tricky part. Now what I want to see if our algorithm can synthesize outputs which are larger than the input. So we go back to our losses, and we want to see if these losses are well defined if I have an output result which has a different resolution than the input. So let's take a look at the Gramm loss. The Gramm loss involves calculating the L2 loss between two Gramm matrices. Now the dimensions of the Gramm matrix are independent of the image size. They're only a function of the number of features which we have in our CNN, which obviously doesn't change for images of two different sizes. So it means our Gramm loss is well defined if we want to synthesize outputs of different size, of a size different than the input. The smoothness loss is independent of the input image size because it's calculated only on the output image. But our diversity loss is an L2 loss on features which size depends on the image they were extracted from, making this loss sensitive to the image dimensions. In other words, we simply can't calculate the diversity loss between images with different dimensions, limiting our ability to output results larger than our input. Now, the correlation loss matrix size is a function of the amount of the size of shifts which we apply for calculating it. We can calculate two correlation matrices of the same size using images of different sizes by using different shifts. In other words, we can use this insight for tricking the algorithm to think of a correlation matrix calculated on a small image with large shifts as one which was extracted from a large image with small shifts. So in the images shown here on the left, we have a large image and its corresponding correlation matrix calculated using shifts of up to half the image size in each direction, making the correlation matrix exactly the same size of the image. And the right images are a small image and its corresponding correlation matrix, which was calculated using shifts which yield a correlation matrix with the exact same size as the large correlation matrix. So if we use this trick, we by definition get a result different than the input, meaning we do not need to use the diversity loss anymore. So the diversity loss is strong when we want to output images, or I mean, it's helpful when we want to synthesize outputs which are the exact same resolution as the input, but once we want to synthesize something larger, we can simply discard it. And another much more simple trick we can test with is simple toroidal expansion of the features. So a few results. Here are our results using the correlation matrix trick. The interesting fact about these results is that the output preserves the diagonal set of purple tiles, even though we did not tell it to do so in any way. This was really big magic for me. Similarly, the white graffiti on the upper result somehow appears only on the right-hand side of the results. Few more of our results, this time synthesized using toroidal expansions. Notice that we properly cope again with both stochastic and regular textures. Okay, up until now, I only showed subjective comparisons. And what I want to do is present a more objective evaluation called stress testing, which we adopted from Caspar. So stress testing involves iteratively feeding a synthesized texture result as a new input and evaluating after how many iterations the result's quality is simply too bad or starts to break down. We compare ourselves to Caspar and Portilla, and in these slides, the bottom digit indicates the iteration number. So we have first iteration, meaning our first output. We save this output, feed it again into our algorithm, yielding the third column from the left, the second iteration, and so on and so forth, until the 10th iteration. you can easily notice that at the 7th iteration, both Kaspar's and Portilla's results start breaking down, while ours still preserves the texture's properties. And it works both on regular textures and on stochastic textures. Okay, a few limitations of our algorithm. We have a degradation of the results quality along the borders. This is most probably due to the replications applied in the CNN conv layers. We show, in this slide, we show the results from our stress testing in order to emphasize this property. You can see that as the iteration increases, from left to right, the borders lose quality. Another limitation is that on our non-optimized code, the runtimes are quite long, taking about 15 minutes for a 224 over 224 image. It's important to emphasize, though, that once we decide the specific texture we want to synthesize, there is a lot of optimization we can do. There's a lot of redundancy in the neural network, especially if this specific neural network uses ReLU activations, which means we have a lot of zeros or multiplication accumulations which we can discard and seriously speed up this result, but still on our non-optimized code, it's a lengthy process. And finally, and we still feel that the result is less crisp compared to patch-based method. And finally, some images fail to synthesize properly for an unexplained reason. It's the magic of using CNN. We did witness, however, that tweaking the algorithm parameters does improve the results, but we do not want to go in this direction, starting to hand-tune the parameters for each texture is not a real solution, so we need to figure this one out. Okay, so to summarize, we defined a new algorithm for texture synthesis involving 3 new losses, which together enable synthesizing both stochastic and regular textures without the need to explicitly define a scale, and we objectively compare our algorithm and show our state-of-the-art results. Okay.
So we also have time for questions here. Maybe I'll start with one then. I was wondering if you had tried, or if there was some way to take the structure from one texture, but the rest of the stuff from a different texture. Could you combine things in that way?
We did try that.
Yeah.
And that failed colossally. Just to play around, okay? We tried these stuff.
Yeah.
Can't currently explain why, but you get complete rubbish results.
I see. Do you
Sorry.
So you mentioned that you don't need the difference function anymore if your textures are
Sorry,
different.
I can hardly hear you.
I'll come forward. So you mentioned that the different texture scales eliminate the need for the difference function. Is there some relationship between the difference in the size of the textures and how much that gives you different results?
So let me make sure I understand. You were asking about, so first of all, our algorithm doesn't require defining any scale, okay? I hope okay. And your question is, do our results somehow depend on the typical scale of the input?
So I guess kind of if you're asking for an output texture, say only 1 pixel bigger in each dimension, do you still get the same good variation? Is that true of when you're asking for something that's exactly twice the size? Is there's got some kind of relationship between the relative size of the input and the output texture and how different they look?
Yes, I'm not sure I completely figured out your question, but I'll try. Our results, at least subjectively, I don't think the quality of our results depends on the size of the output which we synthesize. Does that answer you?
Sure.
Okay, we can take this offline.
Okay, let's thank the speaker again.
titled Patch-Based Optimization for Image-Based Texture Mapping, and it's by Sai B, Nima Kalantari, and Ravi Ramamoorthy.
Okay. Hello, everyone. Today I'm going to present our work on image-based texture mapping. To model the real world, we need to finish two tasks. The first is to reconstruct geometric models of objects. With the availability of consumer depth cameras, nowadays we can easily scan a scene and produce its geometry using techniques like kinetic fusion. However, only having geometry is not enough. We also need to reproduce high-quality appearance. From a color stream, we can get a set of images taken from different viewpoints. Given these images, ideally, we can project them onto geometry and blend them to produce a nice texture map. However, in practice, there are many problems. First, the reconstructed geometry and the camera poses are usually estimated from noisy data, which are often inaccurate. Moreover, the RGB images from consumer depth cameras typically suffer from optical distortion, and this distortion is not accounted for when we project the image onto the geometry. Let's take the case of geometry for example. Suppose originally we have the accurate geometry as well as two images of the geometry at different viewpoints. For a vertex on geometry, we can get it color by finding the projection on image 1. And similarly, we can get it color on image 2. Since everything is accurate, these two colors we get from image 1 and image 2 would be the same. And we can safely blend them to get the color of the vertex. Now assume that the geometry is inaccurate. Let's look at the intersection of these three with the inaccurate geometry. Obviously, the new vertex will have the same projection and get the same color from view 1. But when it comes to view 2, it will be projected to a different location, which usually have different colors. In this case, if we simply blend these two colors, there will be blurring and ghosting artifacts. The problem is similar for the case of irregular camera pose and optical distortion. Therefore, we know that the input images are misaligned in the case of irregular geometry, camera poses, and optical distortion. As a result, naively projecting and combining the misaligned input images produces blurring and ghosting artifacts, just as the video shows. In this work, instead of projecting and blending the original image, which are misaligned, with respect to kind of geometry and camera poses, we propose a novel global patch-based optimization system to synthesize an aligned image for every input image. The synthesized image has most information of the original image and are similar to them. But it is aligned with each other as a result of our global patch-based optimization system. Given these aligned images, we can safely project them onto geometry and do a simple blending to get a high-quality texture map. This talk is organized as following. First, I will talk about some work related to this topic, and then I will introduce our algorithm. Finally, I will show some results of our method as well as the comparison with our approaches. Now let's see some related work first. Reproducing the full appearance of real-world objects from a set of images has been the subject of extensive research. The main challenge of this method is addressing the inaccuracies of capture and process. Instead of blending the projected images, some approach try to solve this problem by selecting only one view for each face. However, these approaches are not able to handle large inaccuracies in challenging cases and produce visible seams in the final texture map. Another solution for this problem is image alignment. For example, Asiman addresses the misalignment between images by warping one image to the other using optical flow. Since it works on a pair of images and doesn't minimize the distortion globally, so this method is suboptimal. The recent work of Zhou solved our optimization system to find optimal camera poses as well as non-rigid corrections of the input images. So they use local warping to do non-rigid correction which is not able to correct large misalignments. And they produce ghosting and blurry artifacts. In comparison, our system synthesizes aligned images by drawing information from the source images in a patch-based manner, and thus is flexible and able to deal with large inaccuracies. We will show the comparison between our method and the approaches mentioned above later in this talk. Our method is inspired by the recent success of patch-based synthesize in a variety of applications, such as hole filling, image retargeting and editing, style transfer, as well as HDR reconstruction. For patch-based synthesize, we are copying patches from the source image to tagged image. It consists of two stages. The first stage is the search stage, which locates suitable patches to copy. So for a patch in the tagged image, we find a patch in the source image that is most similar to it. The second stage is the voting stage. In this stage, if a pixel in tagged image is covered by multiple patches, we find there are most similar patches in the source image, and we do a voting to determine the final color of that pixel. So that's for relative work. Now let me talk about our algorithm. Let's look at the problem again by studying a simple case. Here we have a rough geometry and two input images, S1 and S2. We illustrated the texture mapping process from a novel view MI. First, we project the image S1 to a novel view and get the projection. And then also, we project the image S2 to the novel view. So due to the inaccuracies in the geometry, camera poses, and optical distortions, the two projected source images are typically misaligned. For example, the inside shows that the positions of the characters AR and GR in the two projected source images are different. Therefore, combining these projected source images produce a texture map with blurring and ghosting artifacts. So to solve this misalignment, we aim to synthesize two aligned images for S1 and S2, which we call tagged images, namely T1 and T2. To reconstruct each tagged image, we keep the overall view appearance of the source image, but move its content to correct the misalignment. In this case, if we project T1 and T2 onto the geometry, these two images will be aligned. Note the difference in positions of GR and AR in the source and tagged images. So in this case, since the projected images are aligned, we are able to produce a ghost-free high-quality texture map by simply blending them. Our main observation is that to produce a high-quality texture map, the tagged image should have two properties. So the first property is that the tagged image should be similar to its corresponding source image. And secondly, the projected tagged images should be photometrically consistent. So we propose a global energy function which codifies these two properties. Now let's look at the first property. To satisfy the first property, we need to ensure that the tagged images should contain most information from its source images in a very coherent way. Here, the coherence means that there's no new structures or artifacts in the tagged image. We use bidirectional similarity proposed by Simakov to meet this requirement, which consists of two terms, including completeness and coherence. Let's look at the completeness first. Given a source image S and a tagged image T, then completeness term measures how much information from the source is included in the target. Let S be a patch in the source image, and T be a patch in the tagged image that is the most similar to this patch. We define the completeness as the distance between S and T. So this is done for all patches in source images. From this, we can see that by minimizing this term, we are ensuring that each patch in source image will have a similar patch in target, and thus enforcing most info in source is contained in the target image. Similarly, for the coherence term, we are trying to avoid any new view structures or artifacts in the tagged image. For each patch T in target, we find its most similar patch in S, and define the coherence as the distance between them. So this is done for all patches in target. By minimizing this term, we are ensuring that most patches in the target come from the source image. That is, no new structure or artifact. Therefore, by combining these two terms, we can satisfy the first property of the target images. That is, target images should contain most information from its source image in a visually coherent way. So patch-based synthesize is more flexible than other image alignment methods, such as local warping, and thus is more suitable to handle large inaccuracies, such as missing geometries. So this video shows the chair and green marker on top. Because of the inaccuracy of the consumer depth camera, the marker's geometry is not reconstructed. So in this case, the texture from the marker should not appear in the final texture map. Our patch-based approach only includes valid information from the source and avoids actual artifacts. Therefore, we are able to produce artifact-free results. Zhou aligns all images by locally warping them, so it includes all of the information from the source in the aligned image, and this is not desirable in the case of missing geometries. Therefore, they are not able to remove the marker from the aligned image and produce results with blurring and ghosting artifacts. The method elevator selects one of the source images for each triangle and can avoid ghosting artifacts in this case. However, this approach is not able to remove the texture of the missing geometry, since it exists in all of the source images. Therefore, this method incorrectly places the marker in the final texture map. So we have just talked about the first term of our patch-based energy function, that is the similarity term. And it ensures that the target images contain most of the information from its corresponding source image in a visually coherent way. We still need to satisfy the second property, that is, the projected target images should be photometrically consistent with each other. Now let's see the energy function for the consistency term. Just as the figure shows, given the geometry as well as the two target images, to ensure the photo consistency between the two target images, the high-level idea is that for current target image, we project other target images to the current view. And then we enforce the consistency by minimizing the L2 distance between the current image and the projected target image. Let's see this part in more details. So for pixel xi on the current image and its color, we find the corresponding pixel on our target image that will be projected to this xi. To ensure consistency, we enforce these two colors to be the same by minimizing their L2 distance. This is done for all target images and for all pixels on the current image. Also, we assign each term different weights. It basically gives the smaller weight to the cameras that look at the surface at a grazing angle and are farther away from the object. For the sake of alternative optimization, we introduce a new variable mi, which stands for the optimal target images at each view. So by minimizing this term, we could ensure that all target images are consistent with each other. In summary, our patch-based energy function is as following. The first term is the similarity term, which measures the similarity between source images and target images. And the second term is the consistency term, which measures the difference between target images. The final energy function is the weighted average of these two terms. We evaluate the effect of enforcing our main properties with the two terms. Only optimizing the first term ensures that the target image contains most of the information from the source image. However, since the consistency is not enforced, the final texture is not consistent with the target image. On the other hand, by only optimizing the second term, the consistency is enforced, and thus the target image and the final texture are photometrically consistent. However, the target image has ghosted content which does not appear in the source image. So our full approach optimizes both terms and ensures that the targets contain source info and are consistent. Therefore, only our full approach is able to produce a high-quality texture map. So our approach synthesizes aligned images by optimizing a patch-based energy function. And we propose to optimize this energy function with a two-step approach. The first stage is alignment. During alignment, patch search and vote is performed between the source and target images to obtain new targets. And for initialization, we set the target image same as source image. Note that where the source and target images are similar. The target image is reconstructed by moving the source content to ensure alignment. The second stage is reconstruction. In this reconstruction stage, the synthesized images are projected onto geometry and combined to produce texture images at different views. And the textures at each view are used as new target images at the alignment stage in the next iteration. In case the synthesized target images are misaligned, which is usually the case at the beginning of the optimization, this process produces textures with ghosting and blurry artifacts. The next iteration of the alignment process will then try to reduce the misalignment between the targets, which consequently results in a texture map with fewer artifacts after reconstruction. We continue this process of alignment and reconstruction iteratively until convergence. As is common with the patch-based approaches, we perform this process at multiple scales to avoid local minima and speed up the convergence. For more details about optimization, please refer to our paper. Now let's see the results and comparisons to other methods. We compare our approach with 3 other state-of-the-art methods, including the method of image warping with optical flow by Eisenman, single-view selection method by Witcher, and non-rigid local warping method by Zhou. Let's first see the payload scene. We first show the comparison between our method and Eisenman's method. From the insights, we can clearly see that the Eisenman's approach produces ghosting artifacts. That's because they only perform image warping between a pair of images without optimizing them globally, and thus it is suboptimal. Next, let's see the comparison between Witcher's method and our method. The Witcher method selects one view per face by solving an optimization system to hide the seams between adjacent faces. However, their method is not able to produce satisfactory results in this case, since they assign inconsistent textures to some of the adjacent faces, and it produces visible seams and tearing artifacts. At last, the local warping in Zhou is not able to correct a significant misalignment in this case. Therefore, their results suffer from ghosting and blurring artifacts. In comparison, our method synthesizes aligned images and is able to produce high-quality texture maps with no obvious artifacts. Let's examine the house scene, which has complex and inaccurate geometry. Similarly, Eisenman's method produces blurry and ghosting artifacts. And Witcher's method produces tearing artifacts and visible seams around the pillar. And those methods also cannot correct large misalignments and generates blurry textures. Finally, we compare our method against other approaches on the human body scene. So this scene is challenging for all methods since the subject was moving during the capturing process. In this case, Eisenman's method produces ghosting artifacts, and Witcher's method produces visible seams. And Zhou's method produces blurry texture. Where all other approaches produce results with artifacts, our method properly handles all the inaccuracies and generates a high-quality texture. Our patch-based optimization system could also be used in other applications, such as texture hole filling, reshuffling, as well as multi-view camouflage. For details, please refer to our paper. That's all for my presentation on our work. For future work, we would like to extend our system to directly correct the inaccuracies of the geometry and the camera poses. Also, we would like to use our system for wide baseline wheel interpolation. In conclusion, we put forward the first patch-based optimization system for image-based texture mapping, and we propose a simple, iterative two-step approach to optimize the patch-based energy function. The experiments show that our method produces better results than existing techniques. Here are some acknowledgements. In particular, we would like to thank Professor Pradeep Singh for valuable discussions. That's all for my presentation. Thank you for listening.
Questions?
Hi, very nice work. So my question is, have you tried even more difficult geometry? Like, for example, have you tried to scan a human head and try to put the hair as textures on the human head and something else like plants and grass? Have you tried that?
We haven't tried. We have tried on this. I think generally the performance is not that good compared to the results of other kind of things. I think generally the problem that this kind of thing generally has very complex textures, and the geometry is I can see that this is highly inaccurate. Generally, I have tried all the methods in this paper cannot deal with such a kind of things.
Let's go to the back mic first.
Hey, great work. I'm Chong Yi from University of Washington. And can you give us a concept, an idea how robust and how fast the method is?
Yeah, okay. So for robustness, I think this system is pretty robust, and we have done all the experiments using the same set of parameters. And for running time, generally it takes about around 10 minutes to process around 30 input images of 30 full HD input images.
Two questions. So which camera, like the depth camera and the RGB camera, did you use for the data set? And the second.
We use Intel.
Oh, I see. So there's like two inter-sense devices. Which one did you use?
You mean that? Okay, it should be Intel R200.
I see.
Yeah.
And how well does the algorithm works on like quite specular surfaces?
Generally, I think it also works because it's view independent, and this kind of also we give in our system we give the larger weight to the camera that directly looks at the surface at a small angle. So generally, it works. It also works on the specular surface.
Again, two questions.
Yeah.
Number one, when you do the patch mesh, do you use any transformation between patches other than translation?
No, we didn't transform the patches. We directly use the RGB distance as the distance between the patches.
Okay, and so is there any limitations to the errors in image locations?
Yeah, okay. For limitations, I think generally the patch-based method will sometimes will not well preserve the semantics of the original image. That is, it will be in case of the geometry is highly accurate, it will remove the blurring, but generally sometimes the semantic things the semantics will not be well preserved. So this is some limitation.
Thank you.
Let's thank the speaker. So this paper is titled Globally and Locally Consistent Image Completion, and the authors are Satoshi Iizuka, Edgar Simosera, and Hiroshi Ishikawa.
Thank you. This work was done with these Satoshi and Edgar, and I'm only the third author. But these two found out about a week ago that they couldn't come. They were looking forward to give this talk, but you only get me, so bear with me. So, image completion, also called inpainting, is one of the popular topics in computer graphics and computer vision. It allows filling in a part of images with alternative contents. This technique is, for instance, used for removing unwanted objects or generating occluded regions for image-based 3D rendering. Most successful approaches for inpainting so far have been patch-based. These techniques synthesizes textures by collecting small image patches from the other regions based on global optimization. However, this method has some difficulties preserving the global structures of scenes. For example, in this pair of images, trees and grass appear in midair. This is a typical failure case of the patch-based approach. Additionally, the patch-based methods cannot generate novel objects since the synthesized texture is only obtained from the input image. So in this case, Shin is a nose, but it's nowhere to be found in the original image. So the algorithm used her chin instead of her nose. Therefore, more complicated inpainting like this is pretty difficult for this kind of methods. Okay, so recently, Pathak and others proposed a learning-based technique that utilizes CNNs. They proposed a model that directly outputs texture of a whole from an input image and train the model using the generative adversarial network GAM framework. This GAM was originally used to train generative models using CNNs and can generate sharp and natural-looking images. So they use the GAN architecture to improve the quality of generative texture of inpainting. So this is spearheading work and very nice. However, it can has some problems also. It can only accept a fixed image resolution, such as 128 times 128 pixels, with the mask, both fixed position and size, at least as described in their paper. This is strong limitation for the image completion problem in practice, which generally targets arbitrary missing regions in images of various sizes. Also, looking closely, their method tends to generate texture that is inconsistent with input image. So we thought we could improve upon it substantially. This is another example. Okay, so in our work, we propose a novel network for image completion that results in images that are both locally and globally consistent. For this, we construct a completion network that can fill in arbitrary missing regions in images of any size. We use two auxiliary networks to train the completion network to be globally and locally consistent. Our method can generate novel objects, unlike those patch-based methods, that do not appear elsewhere in the image. So, such as face example here on the right. Let me show you the larger version of the image. So you can see on the right-hand side, that's the output, and you can see this is really good result, that you can't really tell which part has been filled in. Okay, so this is a demo of our method. The user specifies a target region, and then the region is filled in immediately. Also, we can inpaint face and hair. The result of inpainting varies according to the shapes of regions specified by the user. Okay, this is an overview of our model. There are three networks in our method: a completion network, a global discriminator network, and a local discriminator network. We use only the completion network for image completion. The other parts, the discriminators, are used just in order to train the completion network when we train this network. Okay, so the completion network is based on a free convolutional network with 17 convolutional layers. The input is an image, and the image itself and the mask, the inpainting mask, and the model output is an image that is plausible only for the masked area. So the pixels outside of the complete region are restored to the input image. Please note that we use dilated convolutional layers in the mid layers, which allows to compute each output pixel with a much larger input area. So this is important for the image completion task, and I will explain this in the next slide. This is an illustration of the spatial support of the completion network. On the left, the pixel P1 is computed from the influencing region in the spatial support omega 1. On the other hand, the pixel P2 cannot be computed since the supporting area, omega 2, does not contain any information outside of the whole. On the right-hand side, by using the dilated convolutions at lower resolutions, the model can effectively see a larger area of that input image. We can also increase the spatial support by adding layers or using larger kernels in convolutional layers. But we found this using dilated layers to be more effective. Okay, now about the discriminators. There are two discriminators. They are convolutional neural networks trained to recognize whether an input image is real or inpainted. The global discriminator takes the entire image as input, and the local discriminator takes an image patch centered around the completed region as input.
just around the hole. These networks are only used to train the completion network, as I said before. During the training, the completion network and discriminators are alternately updated. The discriminators are trained to distinguish fake from real images, while the completion network is trained to fool the discriminators. The discriminators recognize the image using both global and local information of images, and thus the completion network has to learn both globally and locally consistent image completion. We also use MSE loss to improve consistency of completed images. Okay, for training, we use the Places 2 dataset. This dataset contains about 8 million images with various scenes, which will effectively train the completion network to complete a large variety of patterns. We generate random in-painting masks and use them to erase parts of the input images. The completion network is trained to output the ground truth from the input image with the hole. This is the computational time for image completion. It depends on the resolution of the input image, the size of the input image, but not on the size of the region to be completed, not the size of the hole. Even relatively large images can be processed in under a second if we use a GPU. Okay, these are the results of image completion. Our approach can complete a wide variety of scenes, such as mountain ranges, close-ups of walls, and interiors of a room. I will show you the close-ups one by one. So this is a mountain range. This is a landscape also. This one has some big water. And this is the interior with some letters. And this is a wooden wall. And finally, this is some medieval painting. Okay, this is a result of object removal, which is one of the motivations of image completion. It is natural, and it is nearly impossible to identify where an object has been removed. Not that we have anything against French flags. Okay, this is another object removal result. Okay, this is a comparison with existing methods, patch-based methods. The existing methods cannot generate the headphones since it does not appear in the input image. In contrast, our approach generates the headphones. See, this is where it has been inpainted. This is another example of comparison. While existing methods fail to generate wood columns, our method plausibly generates the columns according to the structure of the shed. This is a comparison of training with different discriminator configurations. So if we only use the MSE loss without any discriminators, it always blurs And the result with the MSE with only the global discriminator is pretty similar. And only with the local discriminator, MSE with local discriminator tends to generate sharper texture inside the hole, but it often loses global consistency. In contrast, our full method can fill in the missing region plausibly, both locally and globally. Although our method can generate various textures to complete missing regions in general images, fine-tuning the model using a specific dataset can achieve even better results for more complicated inpainting. I'd like to show the results of the face dataset. The dataset we use contains about 200,000 face images of celebrities. These are results of the face completion. We can see that our approach can realistically complete faces despite large missing regions. These are results of removing sunglasses. Our method achieves such complicated object removal, which cannot be done by patch-based approaches. Not that these eyes are their actual eyes. These are just filled in plausibly. These are typical failure cases of our method. When a heavily structured object is partially masked, it is difficult to reconstruct the original objects. For example, in the top images, our model reconstructs the mountains and trees in the background over the heads of the guards. Okay, so I have presented a novel approach for image completion that produces globally and locally consistent image completion based on convolutional neural networks. We have proposed a completion network that can inpaint arbitrary regions in images of any size. By using the global and local discriminators, it is possible to train the completion network to produce realistic image completion that is both globally and locally consistent. Thank you.
We have time for questions.
Thank you for your talk. I was wondering if you tried it with cartoons or stuff other than photographs, and if it works well in that case.
I'm sorry, you were wondering if
you've tried
cartoons can be filled?
Yeah, cartoons or drawings or paintings.
Well, actually, we had this CVPR paper last week that does just that. In the case of line drawings, we can do it without specifying even specifying the holes. It can automatically identify where lines might be missing.
Okay, thank you.
So we'll go to the back mic, and in the interest of time, we'll take one or two quick questions.
Okay, I was just interested in if you had any intuition about the design of the generator, like why choose that number of layers? Did you try smaller capacity networks and got worse results, or any interesting design decisions in that space?
Actually, I couldn't really hear the question.
Can you say it again?
Sorry, can you hear me? Yeah, I was mostly just interested if you had any intuition about why you picked the generator architecture that you did, why that number of layers, etc.
Okay, so the path packet pretty much corresponds to having only the global discriminator. And when we tried, we found that for bigger images, it tends to blur. So we thought we might add another discriminator to locally make it locally consistent. And other hyperparameters like the number of layers and such, we basically just tried many different configurations.
Okay, one last question in the front.
Okay, so what if we want to do the opposite? How do we get this solution to actually put on glasses instead of remove glasses? What would you need to change?
I see. So, yeah, I mean, I don't know, but maybe you can just train the system with a lot of, glassed faces, I guess. I think, yeah, it should work the other way around.
All right, thank you.
Thank you.
Switch it using space on.
Okay, the final paper in the session is titled Nautilus, Recovering Regional Symmetry Transformations for Image Editing, and it will be presented by Michael Lukács.
Thank you for the introduction, Manish. Hello, everyone. My name is Michal Lukács, and I'm here to tell you something about symmetry. Symmetry is one of those weird things that are easy for a human to see, but very difficult for a computer algorithm to detect. In the context of image editing, ignore it at your own peril, because you may get a broken result. What's more, it tends to be broken in such a way that is immediately apparent to a human observer. If, on the other hand, we can detect symmetry, we can employ it to support all sorts of interesting applications, such as edit propagation. If we are able to detect the exact parameters of symmetry, even under perspective distortion, we can use this knowledge to remove perspective distortion. And furthermore, if we are able to judge exactly which regions of the image are symmetric, we can use this information to support operations like segmentation. So to summarize, what we are aiming to detect are pixel-perfect transformations describing a symmetry that can include translation, rotation, scale, reflection, and perspective, and to determine exactly where and how accurately this symmetry applies in the image. Furthermore, our system needs to have some built-in tolerance to image irregularities, but on the flip side, we do not want to swamp the user with symmetries that are extremely localized or too general to be useful for edits. For example, the Eiffel Tower is reflectionally symmetric. On the other hand, you can also make an argument that it's translationally symmetric. Technically, this is true within a certain tolerance, but this other symmetry is not accurate enough to be useful for image editing applications, so we need to take some effort to filter out these symmetries. We were inspired by previous work which tackles translational symmetries through self-similarity search. Patch match can find local correspondences, which can then be plotted, and the histogram of these offsets reveals the symmetries. Essentially, each of these peaks you see in the histogram on the right is a symmetry. This is ingenious because it demonstrates that we can mine symmetries from local correspondences. However, this approach handles translations only. So our question was, can we extend this to generalized transformations if we use generalized patch match? So we generalized this pipeline. The first two steps, finding matches and aggregating them, are conceptually similar to previous work, only generalized to handle these generalized correspondences. In addition, we add two more steps to achieve the goals necessary to support our applications that I talked about earlier: support detection and symmetry filtering. First of all, we search for generalized patch correspondences within the image. We use generalized patch match to search over translation, rotation, scale, and reflection to find matches for each patch and measure their L2 distance to rank them. Unfortunately, adding these parameters generates a lot of semi-spurious results. They look okay from the metric point of view, but do not represent a symmetry. Therefore, we modify the search to look only for correspondences that are repeatable. That is, the transformation associated with the correspondence needs to be able to be applied again and still yield a good match in the L2 sense. We do this by modifying the distance function to only consider the greater of these two distances. Thus, we can be sure that all the good correspondences that we detect represent a symmetry. However, in doing this, we've built ourselves a much harder search problem. Initially, the search could take hours to find good results, and sometimes randomly didn't converge at all. This is caused by the curse of dimensionality. If we illustrate the problem as finding the transformation that will map this pink heart to the teal one by random sampling, we see that this is fairly easy to do in 1D case. That is to say, we have a relatively good chance of randomly guessing the correct transformation. However, as we add parameters, we see that while the volume of the search space increases exponentially, the size of the solution space remains about the same. This is always the case in generalized patch match, but in our scenario, this is further compounded by requiring results which are more accurate, which further restricts the size of the solution space. In effect, we are trying to stochastically hill climb a landscape like this. If we start at the yellow cross and sample the search space uniformly, the chances of finding the global optimum here are minuscule. We are in fact much more likely to climb further into this shallow local optimum. What if, however, we could inject external information into the sampling to focus the search on those areas of the search space where we expect the good solutions to be? To do this, we define an oracle function, a simple heuristic that is in our case implemented by comparing only the mean values of the two patches, which is able to discard unpromising matches. We use the Metropolis-Hastings algorithm to bias the sampling towards the area that the oracle deems more promising, and thus increase our chances of hitting the neighborhood of the global optimum, which local search can then easily refine. This change dramatically improved the chances of the algorithm converging. Simultaneously, the new sampling scheme consistently yields better search results, both in terms of reconstruction error and mean distance on a same-time basis. Having found the local correspondences, we now only need to aggregate them to extract the symmetry transformations. Would that it were so simple. Unfortunately, with the extra parameters, the histogram is a lot messier, and simply finding the peaks no longer does the trick, which is probably the reason why Ha and Sun didn't just use generalized patch match in the first place. There are thousands of unique correspondences, but most of them are spurious, either from non-symmetric regions or overfitted to small image details or irregularities. And the good ones are only similarity approximations to the true perspective symmetries. And furthermore, there is no way to tell the good matches from the bad ones, because the L2 distance that we measure correlates more with variance within the patch than with anything that we would consider quality. So we need to discover these projective parameters and simultaneously reduce the number of transformations we are considering. We deal with finding the projective components first. We use Lucas-Canada image registration on all non-trivial correspondences, such as this one, to iteratively find their projective parameters and fine-tune the rest. Because Lucas-Conade is effectively gradient descent on parameter space, that means it's both deterministic and local. When we run it on initializations that locally represent the same projective transform, we find that they cluster as they converge to the same result. So to illustrate a cluster such as this one on some actual transformations, we have these three different initializations, similarity transforms from repeatable correspondences. When we run Lucas-Conade, we see them converging to the same result. This demonstrates that they are local similarity approximations of the same projective symmetry in different regions of the image. And we can take advantage of this by running the registration on all initializations simultaneously and aggregating them as they cluster in parameter space. This way, we perform aggregation by descent. Now that we have an idea of how to recover symmetry transformations, we can move on to figuring out where in the image they apply and to what degree. A naive solution would be to just subtract the image and its transform counterpart, but this isn't particularly informative. Measuring fit like this prefers to match flat areas and is tolerant to mismatch of edges and high-frequency features, which is the exact opposite of what we want. If we go to the opposite extreme and compare gradients only, we are in turn ignoring the flat areas, which we also need to be somehow matched. For a functioning compromise, we consider each frequency band separately. We do this by decomposing both images into Laplacian pyramids, comparing the levels separately, and re-aggregating the result. Thus, we get a result that gives the highest confidence when all of the frequency bands match. It is simultaneously robust enough to handle partial matches, whether due to irregularities in the image or suboptimal transformation parameters. Now that we have undetected symmetries along with their confidence maps, unfortunately, we run into the problem I described in the introduction with non-meaningful symmetries that we now have to handle. To illustrate this, converged symmetries are guaranteed to be locally optimal, but that doesn't prevent them from occasionally overfitting on local features or image irregularities. These are top 6 symmetries from the ammonite example, 2 of which are meaningful, but the rest overfits on a particular small group of cells or an irregularity somewhere. Because we couldn't find any single indicator that would distinguish these, in the end we solve this problem by machine learning. We train a support vector machine classifier that pre-selects symmetries presented to the user. Thus ends our pipeline. To prove its functionality, I will now show a sampling of detected symmetries in a variety of images and how we can use them to support various applications. First off, we built a synthetic dataset with isolated symmetry types to verify basic correctness. Our algorithm is capable of correctly detecting symmetries based on translation, rotation, reflection, slide symmetries, and even spiral symmetries, which are, to our knowledge, not handled by other approaches. We took advantage of having this synthetic dataset to artificially introduce faults into the image. This way, we were able to verify robustness to spot noise of various frequencies, random distortion of varying magnitude, to which we found our algorithm to be particularly robust. Initially, I really wasn't expecting it to work on this, and perspective distortion. In the way of natural images, we can accurately detect symmetries even when the image is cluttered with distractors. Here, we detect a particularly challenging symmetry. Firstly, this is a spiral symmetry. It is further irregular because the cells do not follow a perfect exponential sequence and their shape doesn't quite match. In this image, we detect a translational symmetry under perspective projection. As an additional compounding factor, we have a nonlinear symmetry on the cylindrical tower, but we can still extract the basic translation. And here is another example which combines rotation, perspective projection, and a significant occluder. In terms of applications, here we demonstrate the use of our method for inpainting. We detect translation under perspective, the perspective jointly with the symmetry, not requiring external rectification. If we then want to remove the window, we find that because the detected symmetry is pixel accurate, there is no need to even run a painting algorithm. We can simply stitch the images together. In this example, we use the detected rotational symmetry to segment the image and leave only the non-symmetric region. And because we detect projection jointly with other parameters, we can then decompose the transformation matrix into projective and non-projective components and thus effect rectification. And finally, to show off our teaser, we can do things like detect the spiral symmetry in this perspective distorted ammonite, rectify the ammonite, and also use the transformation to propagate edits along the shell cells. Ultimately, we developed an all-in-one symmetry detection system which discovers generalized symmetries under perspective by analyzing and processing patch correspondences. In doing so, we have learned a couple of interesting things. Through importance sampling, we can inject external information into patch search to help convergence in particularly difficult scenarios. We can make sense out of a noisy correspondence histogram by fitting the candidate transformation to larger regions and aggregating them along the way. And finally, distinguishing matches as good or bad is an open problem, both on patch level and on whole image level. Solving this problem, perhaps with a neural network, could facilitate and improve a lot of applications, both within correspondence search and downstream. So that's it from me about Nautilus. I thank you for listening, and I will now accept your questions.
Maybe I'll start with one quick one. So I didn't see it. Did you talk about the running time of the algorithm?
So the running time is one of our pain points. Right now, the descent is about 40 seconds per symmetry, so the total runtime varies wildly with how many symmetries we detect. There are things we can do to improve that. For example, the descent is almost embarrassingly parallel, and we're not taking advantage of that at all. And there are more aggressive clustering schemes that we've already tried employing to cut down on the number of symmetries. What would really help would be if we had the ability to already sort the candidates into promising and unpromising one, which so far we only do at the end of the pipeline using the SVM.
Hi, great work for a pretty complex problem, so impressive.
Thank you.
Have you evaluated or tested or have a measure of how robust you are to variation within each instance that is symmetrized or repeated? I'm thinking of, I know you have a building with windows which have different reflections, but as humans we perfectly understand they are windows. Do you have a measure of that, or have you tested these things?
So empirically, it tends to work with windows. We haven't done this exact test on this isolated parameter because we weren't able to really figure out a way to quantify that. What we have for synthetic tests is that random distortion, although you could probably design a test that is something like that.
Okay, thank you.
One last question.
The list of symmetries you gave were rotation.
Excuse me, I can't understand what you're saying.
Sorry, better?
Yes.
The list of symmetries you gave were rotation, scale, and spiral, as well as translation. However, those don't seem to add up to include perspective. But your algorithm works well with perspective. I was wondering if you had any insight why you're able to capture perspective. Why you're able to be so robust with perspective without the transformations that include it.
So if there is perspective in the image, we can't directly search for it in the patch search phase, simply because the patches aren't large enough to adequately capture it. So what we rely on is that even when there is perspective, it can be in individual regions of the image approximated by a rigid transform, say, and we are usually able to find that and join these partial approximations after the fact.
Someone who's gotten burnt by perspective when trying those transforms, I'd say it's very impressive. Thank you.
You're welcome.
Okay, thank you. And thanks to all of you. The authors will be here at the front of the room for a little bit after the session.